Welcome, calculus students. Today our lesson is called Maclaurin Series, which goes right in hand with the lesson we did last time, which was on Taylor and Maclaurin Series. You definitely need to make sure that you memorized the 4 series that we talked about in the last video lesson before beginning this one, because this one is going to build upon that information and knowledge. So we are going to learn how to generate some Maclaurin series using the information we learned last time. It says generate the first 4 non-zero terms and the general term for each of the following functions. So this first one has f of x is equal to the sine of 3x all divided by x. So you're going to think about the Maclaurin series for the sine of x, and what we're going to do is everywhere that you would normally have the x in the Maclaurin series, you're going to replace it with a 3x in its place. It's like a composition. And then you're also going to multiply the entire thing by 1 over x. So 1 over x is going to get multiplied by, remember your first term is x, so that's going to be replaced with a 3x. And then it's a negative x cubed, so it'll be 3x quantity cubed over 3 factorial plus, normally it would be x to the 5th, so we're going to do 3x, the quantity 3x raised to the 5th power divided by 5 factorial minus, normally it would be x to the 7th, but we're replacing the x with 3x raised to the 7th power over 7 factorial. And then we go plus dot dot dot, and it continues. So we will go ahead and simplify this out. So I'm going to distribute this 1 over x. So I'm going to have 3x over x minus 3 cubed. I'm just going to leave it with the powers instead of raising them to the powers, because when you start getting to like 3 to the 7th, it's kind of challenging. So we'll go x cubed over 3 factorial. Oh, we also have the 1 over x. So we'll go 3 factorial times x on the bottom plus 3 to the 7th, x to the, I skipped the 5th one. 3 to the 5th, x to the 5th, over 5 factorial times x, pardon me, minus 3 to the 7th, x to the 7th, over 7 factorial times x, plus dot dot dot. All right. Can you see that? There we go. So now I'm going to simplify this. X divides out an x, so the first term is just going to be 3 minus, we'll have 3 cubed and then x squared, because the x cubed divides out the x, over 3 factorial plus 3 to the 5th, x to the 4th, divided by 5 factorial, again because that x to the 5th divides out this x, minus 3 to the 7th, x to the 6th, over 7 factorial, plus dot dot dot. Now for the general term, I'm going to go ahead and write it in sigma notation. The sum from n equals 0 to infinity. Now we have an alternating series, so it's -1. I want this first term to be positive, so I can just raise it to the n power. And then we have odd powers on the 3's. So it's 3 raised to the, starting with a power of 1 when n is 0. So we'll say 2n plus 1. And then times x to the, it would just be even numbers. So starting with 0, that'd be to the 2n. And then we'll divide all of that by the same thing as the power on the 3, which is 2n plus 1 in parentheses factorial. So there's our general term that's written in sigma notation. It would also be okay to list the first 4 terms plus dot 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 plus this general term plus dot 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 again. Okay, so that first one is done. So you can see we handle the composition by substituting something in place of each of the x's in a known Maclaurin series. And we also handled a, you can consider it a product or even a quotient because we divided everything by x or we multiplied it by 1 over x, kind of the same thing. All right, so what are we going to do on the next one, number 2? We have e to the power of x squared. So this is another composition. So we're going to start with our general rule for e to the x, which is 1 plus, normally it would just be x, but we're replacing it with x squared, where the x is, plus, normally it'd be x squared over 2 factorial, but we're going to put x squared in parentheses, then square it over 2 factorial. And then we have plus, normally x cubed, but we'll have x squared cubed over 3 factorial. Plus dot dot dot. Okay, so now we're going to simplify this. So we'll have 1 plus x squared plus x to the 4th over 2 factorial. Remember, when you raise a power to a power, you multiply the powers. So then it's plus x to the 2 times 3, which is 6 over 3 factorial plus dot dot dot. And now we're going to write a general rule in summation notation from n equals 0 to infinity for this new series. So it would be powers of x in the numerator, even powers, starting with 0. So x to the 2n divided by, this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, so n factorial in the denominator. All right, number 3. This one, f of x is equal to x squared times the cosine of pi x. So we're going to use the general Maclaurin series for cosine of x, but everywhere we find an x, we will replace it with pi x, and we'll distribute an x squared to each term. So I'm going to put x squared in front, and then our first term of our cosine Maclaurin series is 1, then it's normally minus x squared over 2 factorial, but we're replacing the x with pi x. And then the next term is normally positive x to the 4th over 4 factorial. We're replacing the x with pi x to the 4th over 4 factorial. And then we have, minus pi x raised to the 6th over 6 factorial. All right, so now I'm going to distribute the x squared to each term. And if you will, I'm going to go ahead and apply the powers to both of the elements inside the parentheses also simultaneously. We're going to do a little bit of work here. So I'm going to have my first term is x squared times 1, so just x squared, minus, it's going to be pi squared, then this is x squared multiplied times x squared, so that's x to the 4th over 2 factorial, and then I have plus pi to the 4th, and then this is x to the 4th times x squared. When we're multiplying and we have the same base, we add the powers. So 4, 5, 6, x to the 6th over 4 factorial, minus pi to the 6th, x to the 6th times x squared is x to the 8th, adding those powers, divided by 6 factorial plus dot dot dot. Okay, so now I need to come up with a rule, a general summation rule that will produce this new series. So I've got powers, well, I've got an alternating series starting with positive. So I've got -1 to the n. Then I have pi raised to even numbers, pi to the 2n, starting with 0, 2, 4, 6. And then I have x is also even powers, but it's 2 more than whatever the power is on the pi. So 2n plus 2, all divided by the factorial matches the power on the pi. So 2n in parentheses factorial will do that. All right. Next, we're going to do number 4. F of x is equal to x divided by 1 minus x squared. So this one is kind of like the 1 over 1 minus x. If you were to multiply everything by an x and replace the x's with x squareds. So it would be 1 plus, normally it'd be x, so it'll be x squared, plus, normally it'd be x squared, so it'll be x squared quantity squared, plus, normally it would be x cubed, so now it's x squared quantity cubed, plus dot, dot, dot. So when I distribute my x to the first term of 1, I get x plus x squared times x is x cubed, plus x to the 4th times x is x to the 5th, plus x to the 6th times x is x to the 7th, plus dot, dot, dot. Now I need to write my general rule in summation notation for this series. So all I have is x raised to odd powers starting with 1. So if n is 0 to start, then it would be 2 times n plus 1 more. That should get me 1, 3, 5, 7 as I plug in 0, 1, 2, 0, 1, 2, 3. Yep. All right. So that is how we can do composition with our four memorized Maclaurin series, a product and a quotient to create new Maclaurin series from there. Now, the next section is titled Finding the Sum of a Series. So the only series that we have found sums of so far are the geometric series, which we use the formula a over 1 minus r to find the sum of a geometric series, and also the telescoping series. We figured out that whatever the limit equaled as n approached infinity on those actually did give us the sum of the series. So other than those, we haven't been finding the sums of these series, but now we are going to do that with these memorized series. So it says to find the sum of this series. A big hint is going to be to look at the general term. See which one of the memorized Maclaurin series you have learned looks most like this, okay? This one is very much like the e to the x Maclaurin series that you memorized, given that the x value is subbed in with a 3, because normally it would be x to the n divided by n factorial. So instead of x to the n, it's 3 to the n. So the sum of this series would be like, let me see. Yeah, because this numerator is 1 plus 3 squared over 2 factorial plus 3 cubed over 3 factorial plus dot 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 plus 3 to the n over n factorial plus dot dot dot. So you can see this is just the same thing as the e to the x Maclaurin series where you fill in 3's in place of the x's. So if you think about that, it's going to equal e to the x except for replace the x with a 3, so e cubed. The sum of the series is e cubed. That's what it adds up to. Interesting, huh? All right, there are 2 more. I would like to challenge you to pause your video and try them on your own, both of them, and see if you can come up with the sum of the series. And it's okay if you don't get it. You can start the video again and I'll walk you through it. So hopefully you've taken the time to try that out on your own. And hopefully on this one, you're recognizing that this is the exact same thing as the Maclaurin series for the sine of x, except for they have taken out the x's and replaced them with 2. The x value is equal to 2 here. So negative 1 to the n and then x to the 2n plus 1 over 2n plus 1 factorial would be the sine of x Maclaurin series, but that x has been replaced with a 2. So that means that the sum of this series is the sine of 2. Okay, that's what it adds up to. Now, number 7, hopefully you've also given this one a try. This one is the Maclaurin series for 1 over 1 minus x where the x value is equal to negative 2/3. Okay, so you can also think of this as a geometric series where the a value is equal to 1 and the r value is equal to negative 2/3, and use your formula a over 1 minus r to come up with the sum of the series. So then it's 1 over 1 minus negative 2/3. Either way, whether you're plugging negative 2/3 in place of the 1 over 1 minus x series, or whether you're using the a over 1 minus r. It's all the same thing. So we have 1 over 1 plus 2/3, okay, which 1 plus 2/3 is the same thing as 5/3 because 1 is 3/3. So 1 divided by 5/3 is equal to, multiply by the reciprocal when you divide by a fraction, 3/5. So the sum of this series is 3/5. Pretty cool, huh? All right. Here it is, our last series problem. Having, well, for this whole unit, this is my last example. However, it's one of these alphabet soup examples, A, B, C, D, E, lots of parts. So it says differentiation and integration of series. The function f is defined by f of x is equal to 1 over 1 minus x. Write a Maclaurin series for f. Give the first 4 non-zero terms and the general term, and for what values does this series converge? Well, you should be able to do this from memory because this is one of our memorized series. So it's 1 plus x squared plus x cubed plus dot 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 plus x to the n plus dot dot dot. And where does this series converge? This is your geometric series. It converges from negative 1 to 1. And that's all. All right, that was easy. Part B. Use your answer to A to find the Maclaurin series for f prime of x. Give the first 4 non-zero terms and the general term, and for what values of x does this series converge? So we're going to do the derivative. The derivative of 1 is 0. Now that, it says the first 4 non-zero terms, so this one just zeroed out, so we can't really count it. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. I have to go to the next one. It would be x to the 4th here. So 4x cubed is the derivative, plus dot 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 plus the general term, n comes in front, multiplies times x, raised to the power of n minus 1, plus dot, dot, dot. Now, when you take the derivative of a series, the interval of convergence will have the same a and b value as the original. It's just that the endpoints may or may not be included. You have to check the endpoints. So let's look at the endpoints. If I substitute a negative 1 in place of the x, n times negative 1 to the n minus 1. And if I substitute a 1 in place of the x, n times 1 to the n minus 1. We have to consider, would these series converge or diverge? So if you need to generate out a few terms in order to do so, you're welcome to. The negative 1 being raised to powers where n is increasing by 1 each time is going to cause it to alternate positive, negative, positive, negative. And n is the term number. So if we start with 0, we have 0, and then we have 1, and then that's to the 0 power on this negative 1, so that's going to make it a positive 1. And then we'd have negative 2, and then positive 3, and negative 4. And no, this is not converging, this is diverging because the limit is not equal to 0. Remember, the divergence test says that the limit must equal to 0 in order for it to possibly converge, and this limit is the limit does not exist, so that diverges. And here, 1 to the anything power is just 1, so this is basically just the term number, 0, 1, 2, 3, 4, 5, 6. So that's going to infinity, so that limit does not exist, so it diverges also. So the interval of convergence is going to be the same as the original series, just from negative 1 to 1, not including either endpoint. Now, part C says, to use your answer to part A to find the sum of the infinite series. Okay, so if you take a look at this series, this one looks like the derivative of 1 over 1 minus x, which kind of makes sense why they would say use your answer to part A, because we're using the same series. But let's see, if you look at it like this, n times 1/3 raised to the power of n minus 1, because the numerator here would be 1, so that n could just multiply and be on top. So that's what we're looking at. This is the derivative of 1 over 1 minus x. So if f of x is equal to 1 over 1 minus x, that's the same thing as saying 1 minus x to the negative first power. The derivative of that function is negative 1 times 1 minus x to the negative 2 times the derivative of the inside function, which is negative 1, which is equal to negative 1 times negative 1 makes positive 1 over 1 minus x quantity squared. And we need to find the value of this derivative when the x value is 1/3. So if I go such that x equals 1/3, I can substitute 1/3 in place of the x and evaluate this. So this is, wait a minute, I feel like I made a sign error. If only you were here with me, you could help me to locate it. Oh, I see. No. Well, we're going to keep going. 1 over 2/3 quantity squared equals 1 over 4/9, which is equal to 9/4. Okay. And now part D, oops, sorry, my paper's dancing. It says use your answer to part A to find the Maclaurin series for the integral from 0 to x of f of t dt. Give the first four non-zero terms and the general term. For what values of x does the series converge? So this time we're going to take the integral, capital F of x, of the original series 1 plus x squared plus x cubed plus dot 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 plus x to the n. So the integral of 1 is x. The integral of x is 1/2 x squared. The integral of x squared is 1/3 x cubed. And the integral of x cubed is 1/4 x to the 4th plus dot 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 plus the general rule would be 1 over n plus 1 times x to the n plus 1 power, and we would evaluate this from 0 to x, which means I plug in x's for all my x's, which they already are, and then subtract what I get when I plug in zeros for all my x's, so I'd just be subtracting 0. So basically this, whoops, kind of cut off my 1 there, is the first four non-zero terms and the general term. Now, for what values of x does the series converge? We have to consider the endpoints, okay? So we're going to substitute in a -1 and a +1 into our general term. So this will be -1 to the n plus 1. And this one will be 1 over n plus 1 times 1 to the n plus 1. All right, so this one is going to be the alternating comparison to the harmonic series here, just basically the harmonic series with a shift of one term. So this alternating harmonic series, the limit does go to 0 of the absolute value of the terms, and the absolute value of the terms do decrease. So by the alternating series test, this one converges. It converges conditionally. It requires the condition of alternating in order to converge. And then the other one, let's see, this is just going to be 1 divided by n plus 1, because this is always going to be 1 no matter what n is. So that one is comparable to the harmonic series also. So this one diverges because it's not alternating, and the harmonic series requires a condition of alternating in order to converge. So this is a diverging series. So the interval of convergence will include the -1, but not the +1, and that's done. All right, here it is, our last series notes problem. Use your answer to part D to find the sum of the infinite series. Okay, so this one looks a lot like this one. The n plus 1 is on the bottom. The x raised to the n plus 1 looks like it is 1/3. 1 over n plus 1 times 1/3 to the n plus 1. So this is my x. X is 1/3. So I want to think of f of x is 1 over 1 minus x. So the integral of 1 over 1 minus x dx, we're going to have to do a little u substitution, right? U is 1 minus x. The derivative of u with respect to x is -1. -1 du is equal to dx. And so if I integrate 1 over u times -1 du, then I get negative integral 1 over u du, which is negative natural log of the absolute value of, go back to x, 1 minus x. And then I just need to fill in 1/3 in place of the x. So this is going to be negative natural log of the absolute value of 1 minus 1/3. And we know 1 minus 1/3 is 2/3, so negative natural log of 2/3. That's the sum of this infinite series, which is an integral of the Memorize series 1 over 1 minus x. All right. Hopefully you've learned a whole lot about Maclaurin series and you're feeling more and more comfortable with them. Take your time on your assignment. Definitely work with a study buddy. Ask lots of questions if you have them, and get ready for your upcoming test because it is coming up soon. This was the last lesson. So y'all have a wonderful day. Please let me know if you need any help, and bye for now.